Hello everyone, welcome to today's webinar. We want to talk about time history analysis today and how to use RF-Dynam Pro, and we will simulate walking and running across a pedestrian bridge. My name is Schubert. I will demonstrate the webinar today and I will show you the example in RFEM, and my colleague Andreas Niemeyer, he will help me throughout the webinar answering all your questions. This is the model that we look at today. So that's an arc bridge, and the persons we simulate are walking in the center along the bridge here. So we simulate an excitation which is changing in time, but also changing in position. So that's the important bit today. This is the GoToWebinar control panel that you all should see, and you can show and hide the control panel by clicking the orange button up here, and you can use the edit field down here to ask questions. Andreas will try to answer all your questions throughout the webinar. Just in case there are too many questions coming in, you get definitely an answer, but it might be via email after the webinar, but we try to be as quick as possible. So let's start with the content. I will first give you an overview and explain the features of the RF-Dynam Pro modules. We will then have a detailed look into time history analysis and how this is implemented into RF-Dynam Pro. We then already have a look into RFEM and we'll have a look to the model of the arc bridge. I will show you quickly how this was done, and we will study the natural frequencies and the mode shapes of the structure. This is important to decide whether or not we have to consider dynamics and which mode shape is the most relevant one. Then we go back to the PowerPoint and we will have a look into theory. So how is the process of walking defined? And we, as I already said, we want to consider as time and position dependent. So we study this then all in RFEM, so we apply all the theory on the example. We will define load cases with another add-on module which is called RF-MOVE Surfaces. So this is just an easy tool to create load cases. You can do this manually also, but this is just a bit quicker using this add-on module. We will define parameters. We will use parameters quite a lot today to make everything quite flexible, because the input it's quite an effort to do all the input today. You will see this in the example, and that's why it's really important to use the parameters to keep it flexible afterwards so that you can change things easily afterwards. We will input time diagrams, and we will use it's still a quite new feature, we will use the direct input of function terms, where you can use the parameters that you have defined. And we have to connect the time diagrams then with load cases to define the position of the excitation cases. And of course, we will analyze the results and study this. We will compare this detailed analysis with a simplified way to analyze all this. You can neglect the position dependency, and this is what we want to do. We want to compare the details study where we study the time and the position dependency, and we will have a look to time dependency only. Last, I will explain the theory of running. So I will show you all the formulas you need to simulate running, but we don't do this as an example again in RFEM because the input would be very similar. So that's why I just show you the formulas and how you can do this. So this is the content. So now you know what to expect, and we start with the overview of the modules. So we have 3 dynamic modules in RFEM. This is the same in RStab. So we have 2 program families. This is RFEM and this is RStab. And dynamic modules exist in both, and they are very similar in both. And in RStab, you can only consider members, and in RFEM, you can also consider surfaces and solids. So this is the main difference between. But the module, the dynamics modules itself are very similar. So this webinar is also useful for RStab users, not only for the RFEM users. So we have the module RF-Dynam Pro Natural Vibrations. which you can use to analyze frequencies and mode shapes for member surfaces and solid models. You can directly import the masses from load cases. You can combine these mass cases in mass combinations. You can also import stiffness modifications, so for example, to consider the pre-stress of cables, or you can deactivate some members. You could consider the stiffness from RF concrete, and so on. So this is considered as initial conditions. So the whole dynamic module at the moment is based on linear calculations. We have obviously several eigenvalue solvers available and everything what you kind of expect from a modal analysis. So you get modal masses, effective modal masses, and modal mass factors, and so on. Then we have the module RF-Dynam Pro forced vibrations, which is based on the natural vibrations. So you obviously need the natural vibrations as a basis. This module, forced vibrations, contains both the time history analysis, that's what we want to look at today, and the multimodal and multi-point response spectra analysis. So today we consider only the time history analysis, and I'm also concentrating here on the introduction only on this one. So the response spectra analysis is to perform an earthquake analysis. This is just a preview of the time course monitor. We will see this later on in the example again. So this is how you can see the results in graphs versus the time. And then we have the module RF-Dynam Pro equivalent loads. This contains a multimodal response spectra analysis. So it's again it's the same, but here you get equivalent loads calculated and exported into load cases, which you can use then in RFEM. So like in this little example here. So I don't go into detail to this equivalent load module. There is another webinar available, which I did earlier. So this is about a natural vibration analysis and equivalent load analysis of a framework. And you can just have a look on our website, and you can always see previous webinars. You can just download them or watch them directly as a video. So that's possible with all of the webinars we did earlier on. So as I said, we will have a detailed look into the forced vibrations, into the time history analysis. So we have the direct integration implemented. So we use the implicit Newmark solver. And here also you have different Newmark solvers available in the literature. We use the average acceleration method. So you could have a look in the literature for further details here. So for example, Wilson's Structural Dynamics is just one book I can mention, but there are many good books available about structural dynamics. So very important for the Newmark solver is to have a small time step. So it needs to be small enough to get accurate results. So I come back to this point later on, and I will give some recommendations for the time step. We have the structural damping implemented, so you can choose between the Rayleigh coefficients and the layers damping, so you can enter them vice versa. So this is converted internally, so you can choose whatever you prefer. We present the results in a time course monitor and also in result tables. So the time course monitor, I did show you already this, and we will see it also in the example again. You can export results from single time steps, and you can also export result combinations, which is then an envelope over time. We can do time history analysis of time diagrams. Time diagrams are user-defined excitation functions, and you can either enter them in a tabulated form. So for example, you could import them from Excel, or you can define harmonic functions where you have to provide an excitation frequency in the shift, or you can enter a function term directly, and this is what we want to do today. And you define loads in load cases in the main program RFEM. And this is the point where you define the position of the excitation function. And the big advantage of this is that you can use all loads that are available in RFEM. So you can use nodal loads, member loads, surface loads, but you can also use free and generated loads, which are very flexible in form and size. And this all is then combined with functions varying over time. So this makes the time history analysis very flexible. You can combine several independent time diagrams. So this is also, we will see this today. So with this option, you can simulate excitations that vary over time and position, for example. The second we have available is a time history analysis of oscillograms. So you can either choose an earthquake recording from our library, or you can define the acceleration time diagram yourself, or import it from Excel. And here you have an excitation of supports. So this is not an free excitation somewhere in the structure. It is an excitation of supports, but we have the multi-point option available. So this is similar to the response spectrum analysis. So this is all for the introduction, and we now have a look already into RFEM, and I will show you the model. Here we go. That's the pedestrian bridge we look at today. So the principal beams here are made of steel, and also there are some cross members. There are some cross members. So I have a field length of 2.5 meters here, and the overall length are 20 meters, and the arc is defined as a spline, and this is also a steel beam. And I defined the arc, the rise of the arc, I defined this as a parameter. So here I have the rise of the arc, which I can change to 4 meters, for example, and you see that the rise is just changing. So I already used some parameters in modeling the bridge. I want to undo this. So this is as it was originally. So we will use parameters quite often today, and I used them already in the model. I don't want to go too much in detail here. I defined a thin surface, which is just a thin concrete surface here. This is just a simplified model. Usually you would define an orthotropic surface here. But I need the surface to define my moving loads later on with the add-on module RF-MOVE surface, and that is why I defined a surface. So, and there's also a webinar available about how exactly this bridge was modeled and how the parameters were defined, and this is shown in a webinar called Parametric Modeling of an Arc Bridge. And this is again available on our website. I will show you this at the far end of the webinar. I will show you how you can access the webinars and how you can download them and so on. So this is all about the model. We go into RFEM already. Here we go, RF-Dynam Pro, dynamic analysis. There are several ways to open add-on modules. You can also open them from here, dynamic, and then RF-Dynam Pro. And here you see again the separation into the 3 add-on modules: natural vibration, forced vibrations, and equivalent loads. And we start just with the natural vibration analysis, and we don't need mass combinations today. We keep it all quite simple. I go into the mass cases, and I just want to import the load case self-weight that I defined. And this includes the self-weight of the bridge and another 4 kilonewton per square meter for further footway structure that is not modeled itself, that I just apply as a load. So I import here the loads of the self-weight load case. And this is important to clear this checkbox here, otherwise you would double the self-weight. You can calculate the masses internally if you want. If the model is too big, I don't really recommend this, but you can. This is for double checking the masses you actually import here. You could also define nodal lines and member masses, surface masses, if you need, so you can define them manually to add, for example, something which you not modeled itself or which is not included in a load case. You can add this manually here. So just as an option. So you have several options already here. Then we have the natural vibration cases where we import our mass case and where I want to have a look to the first 10 eigenvalues. And I just apply a diagonal matrix which only considers the masses in translational directions. And I use the Langkos solver, which is recommendable for such size of structure. So it's not as big. It's a quite quick solver here. It's quite fast. Here's the part where you can import the stiffness modifications, as I said in the introduction. But I go more into detail of these natural vibration cases in the other webinar I mentioned already. And I show you at the end that you find it and that you can watch afterwards. So here we go. I just want to calculate the natural frequencies first of all. And so we have the dynamic results available in the main program RFEM. You reach them with this button, that's table 5, dynamic analysis. And you have several drop-downs here. At the moment, we have just one natural vibration case. So that's why the drop-down doesn't contain anything else. So we will see this is increasing later on. And we can select the mode shapes in this drop-down, or we can just go through the table and look to the mode shapes in the graphic. So this is updating automatically. So let's have a look to the first one. This is just the arc is going to the side. And this one is relevant for us. So this is the second mode shape with 3.65 Hertz. And this is the most relevant shape for us today, because this is the shape of the footway. And what we learn also from this mode shape, that our critical load points are in the quarter points of the bridge. So it's not in the middle of the bridge, it's in the quarter points. And the frequency 3.65 Hertz is below 5 Hertz. And this means we have to consider the dynamics. We have to study this. As you all know, pedestrians are walking with approximately 2.5 Hertz. So this is relevant today. Okay. And we can have a look to the other mode shapes just to complete this. So this here's the footway is going down. Here we have a crossing arc. Here this is twisting. The whole footway is twisting. Second mode shape of the arc. And the third mode shape of the footway. And this is drifting away completely here. And this one, and the last one I want to show you is this one. Okay, so quite interesting mode shapes. For us, the most important mode shape is this one. So we go back to the presentation, and I want to come to the details of walking. I start with the vertical excitation, and this is the only we want to model in our example today, because the horizontal excitation is then again very similar, and you will see how much effort it actually is to enter all these functions and so on. So this is the function that expresses the walking. So we have the person is permanently on the ground. That's why we are adding the self-weight of the person. So this is G, the self-weight of one pedestrian. And the walking itself is described by a sinus function consisting of 3 Fourier terms, which these coefficients alpha and phi. And this was all defined by Professor Bachmann earlier on. So this is the graph. So this is the first maximum represents the heel. And the second smaller peak results from rolling over the ball of the foot. So this is the second maximum. And then you always consider the left and right foot walking along. So I show you this formula again when we enter it into RFEM so that you can really follow it. So a walking person is usually is walking with a step frequency between 1.7 and 2.3 hertz, and with step lengths of 60 centimeter to 1 meter. So this is usually the case, and you have to choose whatever is the worst case for your structure. So in our case, we have a field length of 2.5 meter. So for us, we will use a step length of 62.5 centimeter to be exactly in the center of every field. So this is what you have to think about before you actually work out all these formulas. It depends on your structure. The next one is the walking. Walking also leads to some horizontal excitation, which comes from the push of the foot in the direction of walking and from the movement of the upper part of the body transverse to the direction of walking. This is much smaller than the vertical load, and it only considers half of the step frequency because all this is only happening either in the left or the right direction. So I just want to show you here this formula. It's quite similar. It's a sinus function as well. It consists of 3 Fourier terms, and you have the weight of the pedestrian. This is the number of persons. I come back to this later on. We had this in the formula for the vertical excitation as well. I explain this later, how this is calculated or what kind of assumption you have to do here. We don't consider the horizontal excitation in our example today, but this might be quite important, and you have to consider this if your bridge is quite soft in the horizontal direction. So this might be important, but it's too much for this 1-hour webinar today. So that's why I excluded from today's example. As I said, we come back to the number of persons. So it's not that multiple persons on a bridge do not increase the load by the same factor. So these persons are not walking synchronous. They are just walking random. So that's why you don't multiply by 10 because you have 10 persons on the bridge. So that's why in the formula you have the square root of the number of persons. And then you have to think about how many persons are actually on the bridge. So if there are too many persons on the bridge, then you don't consider a dynamic problem anymore. So if you think about a stream of pedestrians or a crowd, then this is not dynamic. This is just these persons are not walking or running anymore. These are kind of moving slowly, statically. We want to consider the dynamic case, and you find several assumptions in different standards. So for example, you have the Eurocode. They suggest 10 to 15 persons, and it also depends if you consider the change in position or not. So we start today with the detailed implementation. We study the change in position, and then I found the recommendation if your natural frequency of the structure is greater than 2.4 hertz, which is the case for us, you have to consider 4 persons walking along the bridge. And in general, the number of persons shall not exceed the number of 9. When you do not consider the change in position, so when you simplify all the calculation, then you need to consider more persons. So then you should consider half a person per square meter, which would mean for our whole bridge that we have to consider 25 persons. But this is not that's not realistic in our case, because our relevant mode shape, as we have just seen, is the second mode shape. So our critical load points are the quarter points, and that's why it's more realistic in our case to consider only half of the bridge. So in the case where no change in position is considered, I would assume 12.5 persons being on the bridge. So this is something, these are assumptions. It's not very well regulated in the standards. Then I already said that the choice of time step is very important. This is kind of a compromise between accuracy of the results versus the calculation time. So the smaller the time step, the longer it calculates, but the more accurate are the results. So, and there are some recommendations available, and you should choose the largest natural frequency of your system that is relevant for the system response, and apply this formula, and then you get a delta t. In our case, we have the relevant frequency of our system is 3.6 Hertz, and this formula leads to 0.014 seconds. The second one, also relevant, is the largest frequency of the excitation function. So not only the structure is important, also the excitation function. And we have an excitation function, the largest one is 6 Hertz. The largest one is 6 Hertz, so we end up with 0.0083 seconds, which is already a bit less. And I did a convergence study in advance to this webinar, and I studied larger and smaller time steps, and I ended up with 0.01 seconds is good enough and leads to accurate results. Okay, this is the choice of time step, and now we go back into RFEM and we'll study this all in the example. So here we go, that's the pedestrian bridge again, and I've said that we will use RF-MOVE surfaces to generate our load. So we have to create load cases representing the left and the right foot. Always left and right, moving along the bridge here. So I go into RF-MOVE surfaces. I've added these add-on modules to the favorites. So you just click right on the module you need very often and can apply here the favorite, and then you have it always on top of the list. So we go into RF-MOVE surfaces. Someone's microphone is switched on. Thank you very much. Okay, so we want to have loads on all of our surfaces. So I apply the checkbox all surfaces here. And this is all I have to do in the general data. The sets of lines. So we have these pictures here that help us to understand what's going on. So I start with the right foot. And I said this early on, we will have a step length of 62.5 centimeters. So this means that the right foot comes to the ground every 1.25 meters. No, that's the step, the moving step, 1.25 meters up here. And I apply also an offset at the beginning and at the end. Here, and I have to choose some lines, select some lines, and I select those lines here. And then I have to define an eccentricity from there. So to define how far away from this line are my persons walking. So in my case, I want the persons walking in the center of the bridge, and I decided to have the feet 30 centimeters apart from each other. This is something you could neglect, but I want to study this today. So I say that my right foot is 1.1 meter from these lines we've just selected. And I have to apply a minus here. This is something you have to try. It depends on the direction of your lines. And my lines are going away from node 20, so that's why I apply a minus here. So this is the right foot. I create a new set of lines, which I call left foot. And this is with the same moving step of 1.25 meters. And now I have a larger offset. This is something you have to try out. This is just because my left foot is 1 time less on the bridge than my right foot. Well, it's just through the process of walking. So minus 1.4, as I said, 30 centimeters apart. Okay, so this is the picture for the eccentricity. So you select the lines and then we define the EY here. Okay, the next one. Oh, no lines have been selected. That's correct. I have to do this. So the next one is moving loads. We have both feet. So this is just the load itself we define here. So both feet, which is a concentrated force. And I want to just define 1 kilonewton here. That is because I want to define all the multipliers and the actual size of my force in the module RF-Dynam Pro, because in RF-Dynam Pro I can use parameters, and this makes it more flexible at the end. So this is why I've decided for a 1 kilonewton here, so just unity, and I apply all the multipliers then later on in RF-Dynam Pro. So this depends on you. You could also define the weight of the pedestrian here, and then you would not define it in RF-Dynam Pro. It's just a multiplication. Okay, and then we define a sets of movement where we define the right foot, and I just choose the right foot and my load we've just defined, and I want to have all these created load cases into the earthquake category. Not because I'm studying earthquake, just to nothing else does really fit. So I have chosen the earthquake, and that's okay. So we know where it's coming from. It's a dynamic study we do here. So I create another set of movement, which is the left foot. Oh. And again, I choose the left foot, and here both, and that's earthquake. And you see now that the current set creates 15 load cases, and altogether we will get 31 load cases. And now I click generate, and I want to exit the module, yes. And now I can show you what we did. We created all these load cases, and this is what I said, it's just a nice tool to make this a bit faster. So what we created is, when we have a look into Z direction, make these tables a bit smaller. And so we see our loads. Yeah, here it's the 1 kilonewton. Oh, okay. So, and now this is the right foot moving along, and after that follows the left foot. We have to connect this then in the right order with our time diagrams. So, okay, that's us done with RF-MOVE surfaces. Now I want to define a few parameters that we need for the definition of our time diagrams. So I go again into edit parameters, and I define here the parameters G, which is a force of 0.8 kilonewton. So that's the self-weight of the person, which we have seen in the formulas, self-weight of person. And we have the N, which are the number of persons, which is dimensionless. So you have quite many different types of unit types available here. And here I've said earlier that we have to consider 4 persons when we consider the change in position. What we do, so we have to apply 4 persons, number of persons. And then we have the step frequency, which is Fs. There's no frequency available here, so but it doesn't really matter in our case, so I just choose dimensionless, and we start with the 2 Hertz. So we study a frequency of 2 Hertz. Step frequency. I just make a note here that this is actually in Hertz, that I don't forget. And this is all the parameters I want to define. And now I can go into RF-Dynam Pro, and we want to study time diagrams. So we activate the forced vibrations module and we activate the time diagrams. And now we have 2 more tabs here, the time diagrams and the dynamic load cases. I show you the time diagrams, and I said in the introduction that you can define it in tabulated form. So you can here enter whatever you want, or you can import it from Excel. You can define a function as periodic, where you have to provide the excitation function and the excitation frequency and the shift. And that's what we want to do today. You can define a function directly here in the edit fields. So when I get started with the right foot in position 1, and I have to enter now the formula, and I start with the sinus function itself and then apply all the multipliers. So it was a 1 plus the first Fourier term starts with 0.4. Then we have the sinus function multiplied with the sinus function of pi 2 Fs and t. So t is the only parameter that you shouldn't use. So you shouldn't define it yourself, because t is used by Dynam Pro as the time. So this is kind of a pre-used parameter. So you are not allowed to use it. When you use it, then Dynam Pro cannot use it anymore, and then you end up with an error. So 1 plus, yes, I have to close my bracket. And a good indication if you're doing things right or wrong is that as soon as you close one term with a bracket or anything, you should see the graph. If you do something wrong, or if you're in the middle of entering something, you don't see anything here in the graphic. So this is a good indicator whether or not you're doing the things right. So that was the sinus. Now plus, so the graph is disappearing again because I'm in the middle of entering something. This is 0.1 multiplied again with the sinus function, pi 4 So now we see the graph again. So already 2 functions are combined. And now the last term, I show you the formula again in a wee moment so that you know what I'm doing here. So that looks already like that what we have seen in the PowerPoint presentation. So I go back to this and I go back to the walking vertical. So this is the function we just apply at the moment. So what I did the term in brackets now, 1 plus, and then I have the 3 Fourier terms, which are the alpha values, the 0.4, the 0.1, and the 0.1. And then I have the 2 pi multiplied with j. J is, it's J. J is just increasing with 1, 2, 3. And then we have the step frequency and the shift down here. So, and now what's still missing is the square root over n and the self-weight of one pedestrian. And here we have to be a bit careful because the self-weight of the pedestrian, we entered this parameter in kilonewton, but internally in RFEM, everything is used in Newton. So I have to divide my G by 1,000 to really get my kilonewton. So this is a bit tricky. You just have to be careful. So I have defined 0.8 kilonewton in the parameters, but internally now 800 newtons are used. So, and then I have the square root over n multiplied, and this is the formula I'm using finally. So I'm just looking up to 0.47 seconds. So this is what one foot is doing. The right foot on position 1 is having the maximum of the heel and the maximum of the rolling over the ball. Okay, and what I'm now doing, I copy this to save some time. I copy this one here with this button. Instead of creating a new one, I always copy it. And I change this to the left foot in position 1. And now I kind of have to shift this further on the timeline. On what I can do to do so, I can use the if function. So if my time is less than the 0.47 seconds that I've just defined as the first maximum, then everything is 0. And if not, then please apply the formula as I did. And as you see nothing, because here we have a maximum time of 0.47 seconds, and I've said in my if function that it's 0 for all t's smaller than 4.7 seconds. So I have to increase the maximum t here to see something, so I end up with 0.97. So that's what I figured out in advance, obviously. So my period is 1 second because I have a step frequency of 2 Hertz. So what I'm doing now is I copy these functions and always increase by half a second if I switch from left to right foot, and by 1 second if so this one here I have to increase by half a second because I've copied the left foot to the right foot. So I change this to 9.7 and this to 1.4. So, and you see what happens, the same function, same look, but just moved further to the right on the timeline. And now I use my left foot and copy this, and this stays the left foot, but on position 2, and the left foot just hits the ground every second. So I increase both by a second. And I do the same with the right foot. It's position 3 already, and I increase both by a second. And last, this one again, position 3, I increase both by a second. And I would need to do this now up to the far end of the bridge, and it takes 15 seconds to walk across the bridge. So I would need to define more than 30 time diagrams now. So this is what you have to do. It's quite easy because it's kind of just in copying and changing 1 to 2 seconds and so on. So it's quite, but I would need to concentrate now, and you would need to watch me doing this by maybe 10 minutes. So I save this now. I open then afterwards a position where I already entered all this, but I did show you the principle. So this is how you can simplify all this, but still, obviously, you have to enter your different time diagrams. But using the function terms and applying the if function simplifies the work quite a bit, I think. If you decrease here the time step, you see more values. You can then export this to Excel or save it or things like this. So now we go to the dynamic load cases, and I show you what's going on here. But here the same, we will start entering everything, and I will then open a ready-made position where I've made all the input. So this is my dynamic load case. This is the walking in vertical direction. And we will apply the direct integration, which uses the implicit Newmark solver, as I explained in the introduction. Here, I will enter the time steps. So as I said, I did a convergence study of time steps, and I came up with this. This is leading to very accurate results. This is fine enough. We don't need any finer time steps here. I want to consider this up to 15 seconds because it takes 15 seconds to walk across the bridge. I want to export result combinations, and I could also generate load cases for the single time steps. This is here. I don't want to do this today, but this is something you could. Then I want to consider a damping. This is just a steel structure, so I don't damp it as much. It's a small damping value I enter here. And this is now the important bit for us. This is the point, the location where we combine the load cases with the time diagrams we have defined. So I choose the first load case, which is my right foot on the position 1, and combine it with the time diagram 1. And then the step 115 combined with the time diagram 2. And the time step 2, the load case step 216, the right foot again on position 2, with my time diagram 3, right foot position 2, and so on. So this is what you have to combine now. 215 TD4, 316 TD5, 315 TD6, and so on. So this is something I don't want to finish here in the webinar, because again, you would just sit here and watch me doing this for maybe 10 minutes. So what I do, I just click OK now to close this, and I've opened another position already. Same bridge, same model, everything done as we did so far. And I show you what I did in Dynam Pro. I already entered all these positions, so we can have a look through. We started with this one, and I stopped with you together here, and I did go ahead then. So this is just moving along the time scale. And I did already prepare the dynamic load cases, so working on the vertical load, where I combined here all the load cases with the time diagrams. The time step, we discussed this. I export result combinations, and I entered the damping here. It's already green. I did the calculation already. It takes maybe 3-4 minutes. We do another calculation today, so you will see how long it actually takes. But to save some time here, it's green, so this green color here indicates that the results are available, and when you right click on this case, you could delete the results, or you could delete the whole case, or you can clear and select this checkbox over here to solve. So we keep it as is. It's green. I click OK, and now I want to show you the results. So I show you first of all the result tables down here. So again, here are the dynamic results, that tables 5, and you have now not only the natural vibration case, we have also the dynamic load case. And we have now, because we did a time history analysis, we have now here all the time steps available, so we could watch all the results for the single time steps, and we can have a look to the dynamic envelope. So here we go. We look at the deformations at the moment, at the deformations U. So we get maximum deformations of 0.45 millimeters, which is reasonably small. And you can here, you see, you have the nodal deformations, you have member internal forces, you have nodal accelerations, and you have nodal velocities. Important here, we have a direct link here from the dynamic tables to the units and decimal places. So, and you come directly into RF-Dynam Pro. Some of the results are linked to RFEM. Depends a bit on in which table you are, but you get always directly linked to the correct table here. Now we are in RF-Dynam Pro in the results, and we could, for example, change our accelerations to millimeter per square second, or we have also the imperial units available, which is inch, feet, and yard. So you can also change it here. We stay with the meter per square seconds because then that's quite easy to compare with the acceleration g, with the acceleration of gravity. And here the same, you can change from millimeter and here. So this is all available. And also here for the masses, you could change it into tons and ounces and so on. Okay, this is just to let you know. You can increase the decimal places. You have the same here for the input data, and you have the same for all the RFEM results in general. So we have here inch, feet, yard. Okay. Very important tool is the time history, the time course monitor, which you find either here or you find it also in the control panel here, time course monitor. So we want to have a look to this. And I created nodes when I switch off the results here. I have to switch on the node numbers, members of, here I created node 6, which is in the quarter point. I created node 11, which is in the middle, and I created node 16, which is here, the 3/4 points. So 6 and 16 are quite likely the nodes where we expect the maximum results. So these are the nodes where we will study now the results. Okay, so these are all interacting. So when I click now on the node 6, my time course monitor is getting ready and it's loading the data from node 6, and I want to see the displacements in Z direction. So we have maximum deformations of 0.4 seconds here. We can also have a look to the root mean square value up to 15 seconds, which is often quite useful, especially when we look to the accelerations. So we will have a look to the accelerations as well, the accelerations in Z directions. We have quite a few peaks when the person is exactly at this position. So the person is walking along the node 6, and this is where we see the peaks now. But when we have a look to the root mean square, it's a quite reasonable low acceleration, which is acceptable. And also the peaks are still quite low and reasonable. So we can have a look to the other nodes as well. You can use the control key on your keyboard to select more than one node. So I could add the node 11, and now you get both on the graph, and I can add node 16. So you end up with a timeline graph here of all the 3 points. And just to show you this again, the displacement in Z direction. So this is what you can have. The accelerations, I want to discuss quickly the limits of accelerations with you. So I go back to the PowerPoint slide, and that's what we have seen already. So limits of accelerations. So there are some, you find different suggestions and different literature. So you have the Eurocode, which gives us a limit of 0.7 meter per square second, which is roughly the 8% of G, which Professor Bachmann provides. Or you have the British standard, which gives this formula. So, and here you see, this is a quite good recommendation from Professor Bachmann. This picture is also from him. So you have the 8% G, which is roughly the 0.7. And just going back to our results, we have peak values of 0.6. So we are below the limits, even with the peak values, which is quite good. And if we just have a look to the root mean square value again, which is just provided for single nodes, then you see we are well below any of any limits. Okay. So this is us now done with the detailed consideration of the walking in vertical direction. So we only consider the vertical case. We did this very exact. So we combined all these load cases with our time diagrams. So we considered the change in position. And now I want to emphasize again, you can use now these parameters that you've entered here. You can change the self-weight of the persons, you can change the number of the persons, and you can change also the step frequency. Because what you have entered in Dynam Pro is now all dependent on these parameters. So you can easily change this and the time diagrams will adjust. So you don't have to enter this all in the column again just because you want to study different things. So this is quite nice. So I really recommend to use parameters. Another thing I want to emphasize is we've defined these sets of lines here for the left and the right foot. And we've defined here the eccentricities, which is the distance between the lines we've selected and our walking person. So, and you can now easily, we've defined a walking person in the center of the bridge, but you can easily change this eccentricity and study persons walking on the left end or the right part of the bridge. So you can easily change this and just generate new load cases, and they are automatically then combined if you use the same numbers of load cases, and you just run the calculation again, and then you can study what happens. Are the results very similar, or is it worse if the persons are walking on one part of the bridge, on one side? So to finish up with this example, I want to compare this detailed consideration with a simplified calculation where we neglect the change in position. So this is, you are allowed to do so. This is a simplified assumption. And I cancel this because I don't want to change anything. We could just study persons kind of going around in circles on one position if you want so. You have to increase the numbers of persons. That's what we've discussed earlier. So I will edit parameters and I will enter a parameter just called all persons basically. And I said it is reasonable that we consider only half of the bridge, so 12.5 persons walking kind of randomly along this half of the bridge here, number of persons. Okay. And we also have to think about again about our mode shapes. So the node number 6 is the critical load position. So I will define a new load case, which I can renumber to kind of separate this here a bit. I call it load case 4T. And I just call it no position change. And I define a nodal load, which is here, new nodal load. And I define 1 kilonewton in Z direction on the global coordinate system. And I apply this on node 6. This is here. Then I go back into RF-Dynam Pro and I define another time diagram. So I create, no, hold on, I copy the first time diagram where I did not use the if function. So I copy this one and I call it no position change. I have this function and all I have to change is here the parameter. And now, so far, we only considered one period of 1 foot. So now it's kind of several persons are going along. And so I would at least consider 2 periods here. So I would increase the max t to 1 second, or you can even study this a bit longer. So, but 1 second at least means we have both feet on the ground. Okay, and now we go to the dynamic load case. We create another load case here. I copy this one. No, hold on, I don't copy this one because I don't want to have this long filled up table. I create a new one and I say no position change. And I just combine the last load case, no position change, with the last time diagram. And again here we only consider this up to 5 seconds now, because the time diagram we have defined is only up to 1 second, so this should be enough. And I create result combinations, and I again enter the damping value here, and I calculate. So we are nearly done. I'm a bit sorry, I'm running a bit late. So you see the time steps counting up here. So that you can imagine, if you choose even smaller time steps, that the time history analysis can be quite time consuming. But it is a very accurate procedure to analyze your structures dynamically. So nearly done. And we have again a look into the time course monitor, and we will watch the node 6. So I go to the DLC2 and I choose again my node number 6. I have a look to the displacement in Z direction. And here you see already we have a far larger maximum deformation, about 1 millimeter instead of just 0.4. And the acceleration is the most important. We have peak values of 1.5 meter per square second, so above the limits we are allowed to. And I can also provide the root mean square up to 1 second, because this is the length of our time diagram. And here also it's far larger. Instead of just 0.09, we have nearly 0.4 meter per square second, which is still below the limits, but quite close. So this is all I wanted to show you. We are finished now with the example in RF-EM. I think this was a quite complex example, and just remember, similar to this, you can do whatever excitations you want. So you can simulate explosions, you can simulate the movement of bells in churches, you can simulate wind excitations, and so on. So you are quite flexible in load definitions and time diagram definitions. I want to have a quick look with you to the running. So just the theory quickly, this is the process of running. So the main difference to the walking is that the person is not on the ground all the time. So it's kind of in the air. So it's losing contact to the ground. So that the force is 0 for a certain period here. But the amplitude when the person is on the ground is larger than when walking. So this graph compares the walking, the FW, with the running, the FR. And here you have a function. You can again apply the if function and the if term in Dynam Pro. So the implementation of this is exactly the same, just using different formulas and different coefficients here. But yeah, it's actually the same. That's why I don't want to do this again now, and we already running late. So this is all I wanted to show you in RF-EM and about performing a time history analysis. I hope you enjoyed it and that you found it useful and interesting. And I just want to finish up the webinar and show you, just emphasize that we have a website. You find us on www.dlubal.com. You can follow us online. I highly recommend the Dlubal blog, which is available here, where we present features or not so obviously things. Every day there's something new posted there. You can always write us an email in case you have questions, or you can give us a call when you have a service contract. And this is the website, and I promise that I show you where you find the webinars. So here on the left-hand side, you can access webinars, and then you have always, first of all, the upcoming webinars are at top, and then you have the previous webinars, and these are the 2 webinars I mentioned. You have the natural frequencies and equivalent static force analysis in RF-EM, where I explain the mode shape calculation of this structure and the equivalent static force analysis, so which is a multimodal response spectrum analysis. And the second webinar I mentioned is the parametric modeling of an arc bridge, where I model exactly the bridge that we have seen today using parameters. So here you get explained in detail how this was modeled, and here also it's a bit deeper look into the RF-MOVE surface that we used today as well. So this is a recommendation. You can have a look to this webinar. And the next one upcoming is in December about pre-stressed concrete. So you are very welcome to listen to this one. And so I thank you again for your attention. Many thanks. And I hope to hear you again. See you the next time. Bye-bye.